A vast cosmic forge creates and destroys stars in an endless cycle. This drama of stellar death and rebirth is the universe's greatest story, and it holds the secret to our own existence. By the end of this journey, you will understand how you are directly connected to the explosive death of a star. We will witness how a star's final moments forge the elements of life and how its corpse can collapse into a mysterious black hole. We will see how the death of one star gives birth to entirely new worlds. What long-standing cosmic mystery has recent astronomy finally begun to unravel? Drifting within the emptiness of space, a colossal cloud of gas and dust begins to glow with an unearthly light. This is a nebula, the universe's own stellar nursery. Within these vibrant cosmic cradles, like the famous Orion Nebula, the raw materials for new stars float in immense, dark clouds. For a star to be born, this cloud must collapse under its own weight. But this requires a delicate and violent trigger. Often, it is the shockwave from a dying star's supernova explosion, rippling through the void for millions of years, that finally compresses the gas and dust. This incoming wave squeezes the cloud, increasing its density and temperature until gravity can take over. Then, the great collapse truly begins. Gravity pulls every particle inward, drawing the cloud into a spinning, flattening disk. At the very center of this whirlpool, a dense, hot core forms known as a protostar. This infant star is not yet a star at all, but a seething ball of potential, gathering mass and heating up for hundreds of thousands of years. The pressure and temperature at its core continue to climb until they reach an unimaginable threshold. At this critical moment, the star ignites. Hydrogen atoms are forced together in a process called nuclear fusion, releasing a titanic amount of energy. This outward push of fusion energy finally balances the inward crush of gravity, and a stable, main sequence star is born. Our own sun began its life in exactly this way, over 4.5 billion years ago. It was forged from the ashes of long-dead stars, a child of that ancient cosmic cycle. This perfect equilibrium between gravity and fusion defines a star's entire adult life, a long, stable period of shining light and heat into the cosmos. But this balance cannot last forever. The very process that gives a star its life also sows the seeds for its eventual dramatic death. The fuel at its core is finite. And when that fuel begins to run out, the star's peaceful existence is shattered, leading to a final act of cosmic transformation. This stable, shining phase of a star's life is a testament to a perfect cosmic balance. Deep within its core, the immense pressure and heat force hydrogen atoms to fuse together, creating helium and releasing the energy that makes the star shine. This outward push from fusion perfectly counteracts the relentless inward pull of gravity. For a star like our Sun, this equilibrium can last for billions of years, a long, quiet adulthood defined by this steady nuclear fire. Astronomers call this the main sequence, and it is where a star spends the vast majority of its existence. We can visualize this entire stellar life cycle on a powerful chart called the Hertzsprung-Russell diagram. It plots a star's brightness against its color, and right down the middle you see a distinct diagonal band. That band is the main sequence, a cosmic highway where most stars reside during their prime. A star's position on this highway is not random. It is determined at birth by a single, crucial factor, its mass. A star's mass dictates everything. Think of it as the size of a car's fuel tank. A small, frugal red dwarf star has very little mass. It burns its hydrogen fuel so slowly and efficiently that it can remain stable on the main sequence for trillions of years, far longer than the current age of the universe. These are the ultimate cosmic survivors, but at the other extreme, a massive blue giant star is a fuel guzzler. Its immense gravity creates ferocious pressure in its core, causing it to burn through its hydrogen supply in a cosmic blaze of glory that may last only a few million years. It lives fast and dies young. This period of stability is not just important for the star itself, it is the essential foundation for life. Astrophysicists point out that this long, predictable main sequence phase provides the steady light and heat required for planetary systems to form and potentially for life to emerge and evolve. Our own solar system was born and has matured during the Sun's main sequence life. This cosmic constancy, however, is an illusion. The hydrogen fuel in the core is finite. And when it finally begins to run out, that perfect balance shatters, forcing the star into its final, dramatic acts of transformation. The star's long era of stability shatters the moment the hydrogen fuel in its core is finally exhausted. This is the critical turning point, the beginning of its death throes. For millions or billions of years, the outward pressure from hydrogen fusion fought gravity to a standstill. Now, with that central fire extinguished, the balance is broken. Gravity wins, and the core begins an inexorable collapse. As the core contracts, it releases a tremendous amount of gravitational energy, heating up to astonishing new levels. This intense new heat radiates outward, pushing against the star's outer layers with incredible force. The outer envelope of the star, no longer held in check by the same equilibrium, responds by swelling to a monstrous size. The star transforms into a red giant, or, for the most massive stars, a supergiant. Our own Sun will undergo this very process, swelling to engulf the orbits of Mercury, Venus, and even Earth. But deep within its shrinking core, a new drama is unfolding. The core's temperature soars under the relentless crush of gravity, eventually reaching over 100 million degrees. At this extreme threshold, a new fire ignites. The helium ash left over from the previous hydrogen fusion is now hot and dense enough to fuse into heavier elements, primarily carbon. In stars similar to our Sun, this helium ignition is not a gentle process. It happens in a sudden, explosive event known as the helium flash, a violent thermal pulse that tears through the core in mere seconds, though it is entirely contained within the star's vast interior. Following this flash, the star settles into a new, more complex structure. It becomes layered like a cosmic onion. At the very center, the core fuses helium into carbon. Surrounding that core is a shell where any remaining hydrogen continues to fuse into helium. In the most massive stars, this process continues, adding more and more layers. A shell of helium fusion might surround a core of carbon fusion, which itself could be surrounded by a shell of hydrogen fusion. This intricate structure represents the star's desperate, last-ditch struggle against total gravitational collapse. It is fusing whatever fuel it can find, creating heavier and heavier elements in a final, furious attempt to keep itself alive. But this is a battle the star is destined to lose. The new fuels it burns are far less efficient than hydrogen, and they are consumed with breathtaking speed. The star's fate is now sealed by the new element forming at its very heart, carbon. What happens next, whether the star finds a peaceful end or erupts in a cataclysm that seeds the galaxy, depends entirely on the mass it gathered at its birth. For a star like our Sun, the final act is one of quiet and beautiful surrender. After its red giant phase, it lacks the sheer mass to force its core to fuse elements heavier than carbon. The star's outer layers, now only loosely bound by gravity, are gently pushed away by the intense radiation from the hot core. These layers drift outward, forming a vast, luminous cloud around the dying star. We call this cosmic artwork a planetary nebula, a name that comes from their round, planet-like appearance through early telescopes, though they have nothing to do with planets. A stunning example is the Ring Nebula, a glowing halo of gas that resembles a celestial smoke ring, all that remains of a star once very much like our own. This expanding shell of gas, painted with ethereal colors by energized elements, will drift through space for thousands of years, slowly mixing with the interstellar medium. But what of the star's heart? The core that remains is a white dwarf. This is no ordinary stellar remnant. It packs a mass comparable to our Sun's into a volume no bigger than Earth. A single teaspoon of white dwarf material would weigh many tons here on our world. This incredible density comes from a state of matter where atoms are crushed together, their electron shells supporting the core against total collapse. This support, however, has a strict limit. A brilliant astrophysicist, Subramanian Chandrasekhar, calculated that a white dwarf cannot exist if its mass exceeds about 1.4 times the mass of our Sun. This crucial threshold, the Chandrasekhar limit, is the line between a peaceful end and a cataclysmic one. A white dwarf resting peacefully below this limit has no further fuel to burn. It is a hot, dense ember of carbon and oxygen that will simply radiate its remaining heat away into the freezing void of space over billions of years, eventually fading to a cold, dark black dwarf. This gentle farewell still enriches the cosmos, as the expelled gases of the planetary nebula carry newly forged elements like carbon out into the galaxy, elements that may one day become part of new stars, planets, or even life. But for stars born with more than about 8 times the mass of the Sun, this peaceful exit is impossible. Their fate is written in a far more violent and spectacular script. For the most massive stars, a quiet fade into a white dwarf is never an option. Their final moments are far more violent, a spectacular self-destruction that seeds the galaxy with the building blocks of worlds. When a star more than 8 times heavier than our Sun exhausts its fuel, the fusion process in its core races all the way to the creation of iron. This is the star's point of no return. Unlike all previous fusion reactions that released energy to hold the star up, fusing iron atoms actually consumes energy. The star's central engine has suddenly switched from a power plant to a power drain. With no outward pressure to support it, the iron core collapses under its own immense weight. In less than a second, a core that was once the size of Earth is crushed into a sphere barely 10 miles across. The collapse halts so abruptly that the infalling material rebounds, sending a titanic shockwave racing back out through the star's layers. This rebounding shock, combined with a flood of ghostly particles called neutrinos, rips the entire star apart in a cataclysmic explosion. This is a core collapse supernova. For a few glorious weeks, this single dying star can shine brighter than every other star in its entire galaxy combined. In the year 1054, Chinese and Arab astronomers witnessed and recorded such an event in the constellation of Taurus. A new star appeared in the sky, so brilliant it was visible in broad daylight for weeks before slowly fading from view. Nearly 1,000 years later, we point our telescopes at that same spot and find the magnificent Crab Nebula, a tangled, expanding web of glowing gas, the scattered debris from that ancient stellar explosion. These cosmic blasts are not all identical. Astronomers classify them into types based on the elements we detect in their light, clues pointing to the specific way the star died. But regardless of type, their role is universal and essential. The ferocious energy of a supernova blast is the only force in the universe powerful enough to forge the very heaviest elements. Deep within that expanding fireball, atoms are bombarded with a flood of neutrons, building up elements like gold, silver, and iodine. The uranium that provides Earth with geothermal heat was born in such an explosion. Every time you look at a piece of jewelry, you are looking at stardust, yes, but more specifically, you are looking at the ashes of a supernova, a relic of one of the most violent events in the cosmos. Yet, even in this utter destruction, something new is born. The explosion scatters this newly forged material across light years of space, enriching vast clouds of gas and dust that will one day coalesce into new stars and planets. And at the very heart of the devastation, the collapsed core of the star remains, destined to become one of the universe's most mysterious and extreme objects. That expanding shell of stellar debris, traveling at millions of miles per hour, becomes a cosmic recycling center on a truly epic scale. We call this a supernova remnant, and its work is just beginning. For thousands of years, this colossal shockwave plows through the surrounding interstellar medium, the thin soup of gas and dust that fills the space between stars. The collision is violent and transformative. The shockwave heats the gas to millions of degrees, causing it to glow in brilliant X-rays, while also sculpting the debris into intricate, delicate filaments. Look at the Cygnus loop, a remnant so vast it appears to be a celestial veil billowing in a non-existent wind. Or Cassiopeia A, whose chaotic knots and ripples tell the story of a star torn apart just 300 years ago. These structures are not merely beautiful relics, they are dynamic and energetic factories. The tangled magnetic fields and accelerating particles within these remnants are the primary source of cosmic rays, high-energy particles that constantly bombard our planet. Furthermore, within the relatively cooler, denser regions of these expanding clouds, something remarkable happens. Atoms of silicon, carbon, and iron forged in the supernova itself can stick together, forming tiny dust grains. This is the birth of new stardust, the raw material for future planets. The most crucial function of a supernova remnant, however, is its role as a stellar midwife. The immense pressure of the expanding shockwave slams into nearby, quiescent clouds of gas and dust. It compresses them, triggering instabilities within the cloud. Just as the shockwave from an ancient supernova likely triggered the birth of our own sun, this new wave of pressure can overcome a cloud's internal support, causing pockets to collapse under gravity. Inside these compressed pockets, new protostars begin to form. This is the ultimate cosmic handoff. The death of one massive star directly catalyzes the birth of an entire new generation of stars, and with them, new planetary systems. Our most powerful space observatories allow us to witness this entire cycle. The Chandra X-ray Observatory sees the multimillion-degree gas, revealing the incredible energy of the shock. The Hubble Space Telescope, with its sharp, visible light vision, captures the fine, glowing filaments of ejected material. Together, they show us the complex physics and chemistry at work, the violent mixing of new elements back into the galactic ecosystem. This enrichment of the interstellar medium is the final, essential step. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were scattered across space by such an explosion. From the utter destruction of a star emerges the undeniable potential for new creation, for new worlds, and for new life. Left behind after the supernova's fury is the star's collapsed heart, a neutron star. This is one of the universe's most extreme objects, a place where the rules of physics are pushed to their absolute limit. When the iron core of a massive star collapsed in that final second, the pressure became so unimaginably intense that it forced protons and electrons to merge, transforming into neutrons. The entire core, a mass greater than our sun, is crushed into a perfect sphere only about 12 miles across, the size of a city. The density is beyond human comprehension. Just a single sugar cube of this neutron star material would weigh billions of tons on Earth, as much as a mountain. This is matter stripped down to its most fundamental components, packed together with almost no empty space. This incredible compression gives neutron stars other bizarre properties. Like a spinning ice skater pulling in their arms, the core's collapse causes it to rotate at a dizzying speed. A newborn neutron star can spin hundreds of times per second. Its magnetic field, also compressed, becomes trillions of times stronger than Earth's. This combination of rapid spin and an immense magnetic field can create one of astronomy's most useful phenomena, the pulsar. As the neutron star spins, beams of radiation shoot out from its magnetic poles. If these lighthouse-like beams sweep across Earth's line of sight, our telescopes detect a perfectly timed pulse of energy with every rotation. These cosmic clocks are so precise that their regularity rivals atomic clocks. The discovery of the first pulsar in the 1960s was so unexpected that astronomers briefly considered the possibility they were signals from an extraterrestrial civilization. The unwavering rhythm of pulsars has given us powerful tools to test the very fabric of spacetime. By carefully monitoring the timing of pulses from a pair of neutron stars orbiting each other, astronomers have been able to confirm predictions of Einstein's theory of general relativity. They observed that the stars' orbits were slowly decaying, and the timing of their pulses was changing in exactly the way Einstein's equations predicted. If the system were losing energy by emitting gravitational waves, ripples in the fabric of spacetime. This was the first indirect but conclusive evidence for gravitational waves, a discovery that earned a Nobel Prize and opened a new window on the cosmos. Neutron stars, therefore, are not just cosmic curiosities. They are fundamental physics laboratories, allowing us to probe gravity under conditions impossible to recreate on Earth. Yet, even a neutron star represents a precarious equilibrium. It is supported against total collapse by a quantum mechanical force between the densely packed neutrons. But this force, too, has its limits. If the collapsing core is too massive, if the weight of more than about 2 or 3 suns is bearing down, then no known force in the universe can stop the implosion. The collapse continues, punching a hole through the very fabric of spacetime and giving birth to an object of infinite density and gravity so strong that not even light can escape. That steady, metronomic pulse from a neutron star creates one of the universe's most reliable beacons, a pulsar. These cosmic lighthouses are born from the most chaotic destruction imaginable, yet they emit signals of astonishing precision. It all comes down to geometry. A pulsar's immensely powerful magnetic field does not align perfectly with its axis of rotation. As the star spins at incredible speeds, these misaligned magnetic poles funnel intense beams of radiation outward. If one of these beams happens to sweep across our line of sight here on Earth, our telescopes register it as a flash. With every rotation, we get another flash, creating the perfectly timed pulses that define a pulsar. The discovery of the first pulsar in 1967 was a moment of pure astonishment for the research team. A graduate student named Jocelyn Bell Burnell noticed a peculiar, repeating signal in her data, a series of pulses arriving precisely every 1.337 seconds. The signal was so regular and artificial looking that the team half-jokingly labeled it LGM1 for Little Green Men. They had to seriously consider the breathtaking possibility that they were detecting a beacon from an advanced extraterrestrial civilization. Of course, the truth was even more remarkable. They had found a natural phenomenon, a spinning stellar corpse just 12 miles wide that could keep time better than most human-made clocks. The engine powering these beams is the pulsar's own rotational energy and its unimaginably strong magnetic field. These fields accelerate charged particles to nearly the speed of light, forcing them to spiral along magnetic field lines and release intense beams of radio waves, light, and even X-rays from the magnetic poles. This incredible precision makes pulsars invaluable tools. Scientists have proposed using the timing of multiple pulsars as a galactic positioning system for future interstellar travel. By comparing the arrival times of pulses from different known pulsars, a spacecraft could theoretically triangulate its position anywhere in the galaxy. Here on Earth, astronomers use pulsars as probes to explore the space between the stars. As a pulsar's signal travels through the thin gas and dust of the interstellar medium, different radio frequencies are delayed by slightly different amounts. By measuring this dispersion, we can map the invisible material drifting between the stars. From a cataclysmic supernova, the universe forges an instrument of perfect rhythm. Yet, this stability is not permanent. A pulsar's spin gradually slows over millions of years as it radiates energy away, and its clock-like pulses will eventually fade. And for the most massive stellar cores, even the neutron star itself is not a stable endpoint. When the collapse continues beyond this point, it creates a gravitational phenomenon so extreme that it challenges our very understanding of reality. But even a pulsar's immense power is dwarfed by another kind of neutron star. A magnetar possesses a magnetic field so powerful it defies all earthly comparison. These are the universe's ultimate magnets, with fields 1,000 times stronger than a typical neutron star and 1,000,000 billion times stronger than Earth's. The force is so unimaginably intense that it can warp the very structure of matter, twisting the shape of atoms into thin, cigar-like rods. This constant, crushing magnetic stress builds up immense pressure on the star's solid crust. Eventually, the crust can no longer contain it. It fractures in a catastrophic starquake, a seismic event of cosmic proportions. This sudden rupture releases more energy in a fraction of a second than our Sun will emit over 100,000 years, all in a blinding flash of gamma rays and X-rays. In December of 2004, a magnetar located 50,000 light-years away, far outside our galaxy, unleashed such a blast. For 0.2 of a second, its gamma-ray flare was brighter than any other object ever recorded outside our solar system. The radiation was so powerful that it actually compressed Earth's magnetic field and ionized the upper atmosphere, a direct and measurable effect from an event halfway across the galaxy. How does a star create such an incomprehensible magnetic field? Astrophysicists believe the secret lies in the first chaotic seconds of the supernova collapse. If the infant neutron star is spinning at an absolutely ferocious rate, perhaps hundreds of times per second, its interior becomes a dynamo of swirling, superheated fluid. This churning motion of charged particles can amplify a pre-existing magnetic field to these ludicrous levels, essentially freezing this immense field into the newborn star during its solidification. Magnetars demonstrate that stellar corpses are not always quiet graves. They can be dynamic, violent, and unpredictably active, capable of reaching across the cosmos to remind us of the raw, untamed forces that govern the life and death of stars. When the final, collapsed core of a star weighs more than about 3 times our Sun, even the fierce resistance of a neutron star fails. Nothing in the known universe can withstand such immense gravitational force. The collapse does not stop at a city-sized sphere. It continues into an infinite descent, punching a hole in the very fabric of space-time itself and creating a stellar mass black hole. At the heart of this phenomenon lies the event horizon, a perfect sphere of no return. It is not a physical surface you could touch, but a mathematical boundary. Once any object, even a particle of light, crosses this invisible threshold, the escape velocity exceeds the speed of light. Since nothing can travel faster than light, nothing can ever come back out. The laws of physics as we know them break down at this point. For any matter unfortunate enough to fall toward a black hole, the experience is both terrifying and bizarre. The gravitational pull on the side of an object closer to the black hole is vastly stronger than the pull on the far side. This difference, the tidal force, stretches the object into a long, thin stream of atoms, a process vividly known as spaghettification. An astronaut would be stretched into a strand of subatomic particles before being crushed into the singularity, the black hole's infinitely dense core. But how can we study something that emits no light? We observe its violent relationship with its surroundings. Many black holes exist in binary systems, locked in a gravitational dance with a companion star. The black hole's intense gravity can pull streams of gas away from its stellar partner. This gas does not fall straight in. Instead, it forms a rapidly rotating structure called an accretion disk, whirling around the event horizon at nearly the speed of light. The friction within this disk heats the gas to millions of degrees, causing it to glow with intense X-rays before it vanishes forever. One of the first and most famous examples is Cygnus X1, a powerful X-ray source in the constellation Cygnus. By studying the orbit of its blue supergiant companion star, astronomers calculated that the unseen object pulling on it must possess about 15 times the mass of our Sun, all confined to a region from which no light escapes. This was the first compelling evidence for a black hole's existence. The formation of a black hole is gravity's ultimate victory, the most complete surrender of matter to its pull. Yet, even in this final state of collapse, these dark remnants are not isolated. They actively shape their cosmic neighborhoods, their gravity influencing the motions of nearby stars and, through their accretion disks, launching powerful jets of radiation that can be seen across the galaxy. The violent spiraling dance of two neutron stars or black holes does more than just release energy. It actually shakes the very fabric of the cosmos. Einstein predicted that the acceleration of massive objects would send ripples through spacetime itself, distortions that travel outward at the speed of light. These are gravitational waves. For decades, they remained purely theoretical, their signals so incredibly faint that detecting them seemed almost impossible. Then, in September of 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history. Its twin detectors, separated by thousands of miles, both registered an identical, fleeting chirp. The signal matched the precise computer model for the final moments of two black holes, each about 30 times the mass of our Sun, as they spiraled into each other and merged. This was the first direct detection of gravitational waves, confirming a century-old prediction and opening an entirely new sense with which to perceive the universe. We were no longer limited to observing light. Now we could listen to the vibrations of space-time. The properties of these waves tell us everything about the objects that created them. From the specific pattern of the ripple, scientists can decipher the masses of the merging objects, their spins, and even their distance from Earth. This gives us a direct probe into the most extreme gravitational environments, places where space and time are warped beyond recognition. But the true power of this new sense was revealed in August of 2017. LIGO detected the gravitational waves of a different kind of collision, not black holes but two neutron stars. Crucially, this event was also seen by telescopes across the globe and in space. For the first time, astronomers could both hear the spacetime ripple and see the brilliant flash of light from the same cosmic catastrophe. The optical observations showed a bright, expanding cloud of material glowing with the telltale signatures of newly forged heavy elements, including gold and platinum. This multi-messenger event provided direct, undeniable proof that the violent mergers of stellar corpses are cosmic forges, producing a significant portion of the universe's heaviest elements. The gold in a wedding ring was likely created in such a cataclysmic collision billions of years ago. With gravitational wave astronomy, we are no longer just watching the silent death of stars. We are listening to their final moments, hearing the echoes of collisions that enrich the galaxy with the very stuff of planets and life. Every single element around you, from the oxygen you breathe to the screen you are looking at, has a cosmic origin story written in fire. This process is called nucleosynthesis, the universe's method of building atomic nuclei, and it is the ultimate source of all the matter we know. The very first chapter of this story began with the Big Bang itself. In the universe's first few minutes, the entire cosmos was a searingly hot fusion reactor. Protons and neutrons collided and combined, forming the nuclei of the lightest elements. This primordial alchemy produced almost all the hydrogen and helium that would ever exist, the fundamental fuel for the first stars, but the universe was still simple. The periodic table was barely started. The creation of everything else required the long, patient work of stars. Inside the stable core of a star like our Sun, nuclear fusion builds elements step by step. Hydrogen fuses into helium. In later stages, helium fuses into carbon, and carbon can fuse into heavier elements like oxygen and neon. This stellar nucleosynthesis is a slow, methodical cookery, but it has a limit. The fusion process only creates elements up to iron. Fusing atoms into anything heavier than iron does not release energy, it consumes it. So how did the gold in a necklace or the iodine in your body come to be? They require a more violent and extreme forge. This is where the rapid process, or R process, takes over. In the chaotic heart of a supernova explosion, or in the furious collision of two neutron stars, atoms are bombarded by a flood of free neutrons. Nuclei greedily capture these neutrons faster than they can decay, rapidly building up mass and transforming into heavy, unstable isotopes. These unstable forms then decay into stable, familiar heavy elements like gold, platinum, and uranium. The R process is a blizzard of nuclear activity, creating in seconds what would take stars billions of years. We are, in the most literal sense possible, made of stardust. The calcium in your bones was forged in the heart of a long-dead red giant star. The iron carrying oxygen in your blood was the final ash in the core of a massive star just before it went supernova. The iodine essential for your metabolism was almost certainly born in the cosmic cataclysm of two colliding neutron stars. Every atom in your body, except for the primordial hydrogen, was created in a star that lived and died before our Sun was even born. This is the profound closure of the cosmic cycle. A star's death is not an end. It is a dispersal, a scattering of newly forged elements that will drift for eons. These atoms will eventually become part of vast molecular clouds, the very nurseries where new stars and planets are born. Our solar system formed from a cloud enriched by countless such stellar explosions. The death of ancient stars provided the raw materials for our Earth and for us. We are the universe's way of remembering its stellar ancestors, living proof of an endless cycle of creation born from destruction. While supernova remnants are the chaotic aftermath of stellar violence, the death of a star like our Sun is a far more serene and artistic affair. These stars do not explode. Instead, they exhale their outer layers into space, creating some of the most breathtaking structures in the cosmos, the planetary nebulae. Their name is a beautiful accident of history. When William Herschel peered through his telescope in the 1780s, these glowing orbs appeared as small, greenish disks, reminiscent of the distant planet Uranus. He called them planetary nebulae, a label that stuck, even though we now know they have absolutely nothing to do with planets. They are, in fact, the final, glowing shrouds of dying stars. The intricate shapes of these nebulae are a source of constant wonder. Not all are simple spheres. Some, like the Butterfly Nebula, form magnificent bipolar structures with two distinct lobes resembling a cosmic hourglass. These complex shapes are often sculpted by a hidden companion star. As the dying star sheds its atmosphere, a nearby stellar partner can funnel the outflow into jets, carving the gas into those magnificent wings. In other cases, powerful magnetic fields, like invisible hands, mold the expanding shell into intricate patterns. The vibrant colors that paint these cosmic clouds come from a fascinating process. At the very center of the nebula sits the star's exposed core, now a searingly hot white dwarf. This stellar ember emits intense ultraviolet radiation, which slams into the slowly expanding cloud of ejected gas. This high-energy light energizes the atoms in the gas, primarily oxygen and nitrogen, causing them to fluoresce with their own characteristic glow, much like the gas inside a neon sign. The famous Helix Nebula, often called the Eye of God, displays this with ethereal blues and reds, a celestial eye staring back at us from across 700 light-years. Yet this beauty is fleeting. A planetary nebula is a short-lived phenomenon, a cosmic firework that blazes for only about 10,000 years before its gas dissipates and fades into the darkness of interstellar space. In that brief time, however, it performs a crucial role. The expelled gases are rich with newly forged elements like carbon, the fundamental building block of life as we know it. This gentle, artistic death is how average stars return their enriched material to the galaxy, ensuring that their legacy will one day be woven into new stars, new planets, and perhaps new life. The serene glow of a planetary nebula is the final, brilliant signature of a star that chose to bow out gracefully, its last breath illuminating the cosmos. That brilliant stellar ember, the white dwarf, is a universe in miniature. It is the exposed core of a star like our Sun, laid bare after its outer layers have drifted away. This Earth-sized sphere contains a mass comparable to our entire Sun, a density so extreme that a single sugar cube of its material would weigh as much as an elephant here on Earth. This incredible compactness creates a state of matter that does not exist naturally anywhere on our planet. The atoms are crushed together so tightly that their electron shells are pressed against one another, creating a powerful outward pressure that physicists call electron degeneracy pressure. It is this bizarre quantum force, not the heat of fusion, that finally halts the relentless crush of gravity, supporting the white dwarf in its final, stable form. Its composition is typically a crystallizing mix of carbon and oxygen, the final ash from the star's internal fusion fires. The white dwarf begins its afterlife as a searingly hot object, with surface temperatures that can exceed 100,000 degrees Celsius. But with no internal energy source left, its fate is simply to cool. It slowly radiates its residual heat into the frigid vacuum of space over billions of years, fading from brilliant white to yellow to a dim red, and eventually to an invisible black dwarf, a cold, dark cinder. Yet our universe is only about 13.8 billion years old, not old enough for even the first white dwarfs to have completed this journey. The cosmos has not yet had time to produce a single black dwarf, but this quiet fade is not the only possible future for a white dwarf. Many exist in binary systems, gravitationally bound to a companion star. If the two stars are close enough, the white dwarf's powerful gravity can begin to steal material, primarily hydrogen, from its stellar neighbor. This stolen gas spirals down onto the white dwarf's incredibly hot surface, where it accumulates, heats up, and eventually ignites in a runaway thermonuclear explosion. From our vantage point, we see a star in that system suddenly flare to incredible brightness, becoming what we call a nova. This surface explosion does not destroy the white dwarf, and the cycle of theft and explosion can repeat every few decades or centuries. However, a far more catastrophic outcome awaits if the white dwarf is too greedy. If the steady accretion of mass pushes it over the Chandrasekhar limit of about 1.4 solar masses, the star's entire structure becomes unstable. The increased gravity overwhelms the electron degeneracy pressure that was supporting it. In a fraction of a second, the core is compressed and heated to unimaginable temperatures, triggering a runaway fusion of carbon and oxygen that rips the entire white dwarf apart. This is a Type Ia supernova, a titanic explosion so uniform in its brightness that astronomers use it as a standard candle to measure vast cosmic distances. These white dwarfs, the long-lasting fossils of stellar evolution, are far more than simple embers. They are potential time bombs, cosmic thieves, and the ultimate cosmic mile markers, their quiet existence occasionally punctuated by some of the most energetic events in the universe. The quiet thievery of a white dwarf can lead to the most precisely predictable explosion in the universe. Picture a binary system where a white dwarf and a normal star orbit one another. If they drift too close, the dwarf's intense gravity begins to siphon hydrogen gas directly from its companion. This stolen fuel flows onto the white dwarf's searing surface, accumulating until the pressure and temperature at its base trigger a runaway nuclear fusion reaction. The entire surface layer of hydrogen detonates in a brilliant flash we call a nova. The star flares to incredible brightness, but the white dwarf itself survives, ready to begin its theft all over again. The real cataclysm occurs if the white dwarf is too successful. If the steady accretion of matter pushes its total mass over the Chandrasekhar limit, about 1.4 times the mass of our Sun, the star's entire structure becomes unstable. The immense gravity overwhelms the quantum forces that were holding it up. In a heartbeat, the core is compressed and heated to billions of degrees, igniting carbon fusion simultaneously throughout the entire star. There is no shockwave to contain it, no structure to resist it. The entire white dwarf is consumed from the inside out in a thermonuclear fireball, ripping itself completely apart. This is a Type Ia supernova. What makes this particular kind of stellar death so special to astronomers is its remarkable consistency. Because the explosion always happens at the same precise mass threshold, and because the object that explodes is always a carbon-oxygen white dwarf of a very specific composition, the physics of the detonation are almost identical every single time. This results in a nearly uniform peak brightness. Think of it like a 100-watt light bulb. Whether you see it in your living room or from a mile away, you know its intrinsic power is 100 watts. If it appears dimmer from a distance, you can use that dimming to calculate exactly how far away it is. Type Ia supernova are the universe's 100-watt light bulbs, its perfect standard candles. This reliability made them the key instrument in one of the most profound discoveries of the 20th century. Two teams of astronomers were using these supernovae to measure the expansion rate of the universe, expecting to find that the pull of gravity was slowing it down. Instead, their data revealed the opposite. The most distant supernovae were fainter than they should have been, meaning the universe was not just expanding, but its expansion was accelerating. Something was pushing the galaxies apart faster and faster, a mysterious repulsive force we now call dark energy. This discovery, which earned a Nobel Prize, completely reshaped our understanding of cosmic fate. In its own destruction, the white dwarf seeds the galaxy with iron, along with silicon and sulfur, scattering these intermediate mass elements far and wide. So these predictable explosions do more than just recycle star stuff. They provide the very yardsticks we use to measure the cosmos, revealing the hidden forces that govern the ultimate destiny of everything we see. Far from being isolated, most stars are born with at least one companion, locked in a gravitational dance that lasts their entire lives. This cosmic partnership can transform a peaceful stellar retirement into a spectacularly violent finale. The fate of these stars is not determined by their own mass alone, but by the intricate gravitational tug of war they share. In a close binary system, as one star ages and swells into a red giant, its outer layers can become so loosely bound that its companion star begins to siphon them away. This mass transfer can dramatically alter both stars' destinies. The donor star can be stripped down to its bare core long before its natural time, while the recipient star, suddenly flooded with fresh hydrogen fuel, is effectively rejuvenated, resetting its evolutionary clock and extending its life. This stellar vampirism is not always a gentle process. In some systems, the transferred material doesn't settle peacefully onto the companion. Instead, it forms a vast, swirling accretion disk of superheated gas, a visible testament to the ongoing theft. The most dramatic consequences, however, are saved for when one star has already died. Picture a binary system where a white dwarf orbits an aging red giant. The white dwarf's intense gravity pulls a relentless stream of hydrogen from its bloated partner. This gas accumulates on the dwarf's searing hot surface until the pressure and temperature at the base of this stolen layer become unbearable. The entire hydrogen shell then ignites in a runaway thermonuclear explosion, causing the system to flare brilliantly as a nova. This surface blast can repeat every few thousand years, a cyclical eruption that does not destroy the white dwarf. But if the accretion is steady and pushes the white dwarf over the Chandrasekhar limit, the result is far more final. The entire white dwarf is obliterated in a Type Ia supernova, a titanic blast that scatters iron and other elements across the galaxy. For even more massive binaries, the end game is even more extreme. Two neutron stars can spiral inward over billions of years, their orbits decaying through the emission of gravitational waves. When they finally collide, the impact is so violent that it forges a flood of heavy elements like gold and platinum, and can leave behind a single, more massive black hole. These cosmic mergers are the source of the gravitational wave signals we can now detect, the ripples in space-time from the most powerful collisions in the universe. From gentle mass transfer to catastrophic mergers, the interactions within these stellar partnerships are a primary engine for the most luminous and element-rich explosions we observe, proving that in the cosmos, death is often a shared and spectacularly transformative experience. This vast repository of stellar material, the interstellar medium, is the true backdrop for the cosmic drama. It is not an empty void, but a dynamic and tenuous mixture of gas and dust that fills the space between the stars. This is the raw material for all future generations, a cosmic ecosystem constantly being reshaped. The interstellar medium exists in several distinct phases, each with its own role. There are vast regions of hot, ionized gas, where atoms have been stripped of their electrons by intense ultraviolet radiation from massive stars. There are warmer seas of atomic gas where single hydrogen atoms drift. But the most crucial for star formation are the cold molecular clouds. These are the dark, dense nebulae, cosmic wombs where temperatures plunge to only a few tens of degrees above absolute zero. Within these frigid, dark clouds, hydrogen atoms can pair up to form molecules, and the gas becomes thick enough for gravity to eventually take hold. Woven throughout all these phases are tiny dust grains, particles of silicon, carbon, and ice only a fraction of a micron in size. These motes of dust are not just passive observers. They act as miniature shields, blocking starlight and allowing the interiors of molecular clouds to remain cold and dark, a necessary condition for collapse. They also provide surfaces where simple chemical reactions can occur, eventually forming complex molecules, including the precursors to life itself. This entire ecosystem is continually enriched and energized by the death of stars. The shockwaves from supernova do more than just trigger collapse. They blast newly forged elements like oxygen, carbon, and iron directly into this medium. Similarly, the powerful stellar winds from massive, short-lived stars push their own outer layers into space, seeding the clouds with heavier elements. This process, repeated over billions of years and countless stellar generations, is what transformed the primordial universe of simple hydrogen and helium into the chemically rich cosmos we see today. It is this enrichment that made the existence of rocky planets like Earth and the life upon them possible. The interstellar medium is the universe's grand recycling center. The iron in your blood was once part of the interstellar medium, enriched by a supernova long before our sun was born. The oxygen you breathe was forged in a star and then cast off, destined to become part of a new stellar nursery. We are not just made of stardust, we are made of stardust that has been through this cosmic cycle countless times, the legacy of generations of stars that lived, died, and scattered their essence back into the galaxy, setting the stage for everything that was to come. Deep within the vast expanses of the interstellar medium lie the true stellar nurseries, colossal structures known as giant molecular clouds. These are not the glowing, ethereal nebulae we often see in photographs, but their dark, dense hearts. The Orion Molecular Cloud Complex, a mammoth structure lurking behind the familiar glow of the Orion Nebula, stretches for hundreds of light years. It is a realm of profound cold and shadow, where temperatures hover just a dozen degrees above absolute zero. In this deep freeze, individual atoms can link together, forming molecules like molecular hydrogen, the primary ingredient for new suns. Despite their immense mass, these clouds do not instantly collapse into stars. They are held in a fragile equilibrium by a combination of internal turbulence, which acts like a constant stir, and magnetic fields that thread through the gas, providing a supporting structure against the relentless pull of gravity. For a star to be born, this balance must be violently upset. The trigger often arrives like a cosmic hammer blow, a shock wave from a nearby supernova explosion that has traveled for millennia. This incoming wall of pressure slams into the cloud, compressing the gas and dust, creating dense pockets where gravity can finally gain the upper hand. As these regions collapse, they do not form single stars, but instead fragment into smaller and smaller clumps, each one a potential stellar seed. This is why stars are almost always born in clusters, as entire families emerging from the same dark womb. The brilliant new stars we see lighting up nebulae are just the visible evidence of this deeper, darker process. The formation of a star cluster is therefore a direct inheritance, a cosmic gift of raw materials and the necessary push, delivered by the explosive death of the generation that came before. Within that collapsing fragment, a new world takes shape. The dense, hot core at the center is now a protostar, but it remains hidden, shrouded by the very cloud that gave it birth. This infant object is not yet powered by nuclear fusion. Instead, it glows with the intense heat of its own violent contraction. radiating the gravitational energy released as it continues to crush itself smaller and denser. It is fed by a swirling, flattened disk of gas and dust that orbits it like a cosmic carousel. Material from this disk spirals steadily inward, raining down onto the protostar and increasing its mass. Yet this feeding process is not neat or orderly. As the star and its disk spin, twisted magnetic fields channel some of the infalling material and blast it back out into space. These are bipolar jets, two narrow, supersonic fountains of gas that erupt from the protostar's poles, shooting light years out into the surrounding nebula. They act as a release valve for the system's excess spin and energy, carving through the cloud and revealing the violent dynamo at its heart. We can trace the protostar's evolution on the Hertzsprung-Russell diagram, following its path toward true stardom. At first, it is large, cool, and very luminous, contracting rapidly. This phase places it on what astronomers call the Hayashi track, a nearly vertical descent on the diagram where the protostar shrinks without a significant change in its surface temperature, glowing a deep, cool red. Once its outer layers become more transparent, allowing heat to escape more efficiently, the contraction slows and the object begins to heat up significantly. This shift moves it onto the Henny track, a more horizontal path across the diagram toward higher temperatures. The star is now a pre-main sequence object, no longer a hidden protostar but a visible young star, still contracting and heating up on its final approach to ignition. This final stage before true stardom is marked by intense and erratic behavior, known as the T-Tauri phase. Named for a variable star in the constellation Taurus, these youthful suns are famous for their powerful stellar winds, hundreds of thousands of times stronger than our sun's solar wind. They flare unpredictably, their brightness changing dramatically over days or weeks as massive star spots rotate across their surfaces and immense magnetic loops reconnect. This tempestuous period is also the crucial epoch of planet formation. Within the calm midplane of the circumstellar disk, the dust grains begin to stick together, colliding to form pebbles, then rocks, and eventually the building blocks of planets. The fierce T-Tauri winds will soon blow away the remaining gas in the disk, ending the star's main course of accretion and halting the growth of gas giants. The emergence of a stable star from this chaotic birth is the start of a new cosmic era, one where the leftover material from its formation can coalesce into new worlds, setting the stage for the next great act in the universe's endless cycle. Our own sun provides the most intimate portrait of this stellar journey, a slow-motion destiny shared by countless stars across the cosmos. Its story began over 4.5 billion years ago within a cold, dark molecular cloud. That primordial cloud was not pure. It was already salted with heavier elements like silicon and iron, the legacy of supernova that had exploded in our galactic neighborhood long before. A shockwave, perhaps from one of those very explosions, triggered the cloud's collapse, spinning it into a flattened disk we call the solar nebula. The vast majority of the material fell to the center, heating up until nuclear fusion ignited and our sun was born. The leftover crumbs in the surrounding disk eventually clumped together to form Earth and all the other planets. This is why we can say with certainty that we are the children of long-dead stars. Today, the Sun is in the prime of its life, a stable main sequence star. For the past 4.5 billion years, it has faithfully converted hydrogen into helium in its core, providing the steady, gentle light that allowed life to flourish on our world. This equilibrium is a cosmic gift of constancy, but it is temporary. In about 5 billion years, the hydrogen fuel in the Sun's core will finally be exhausted. With a central fusion engine sputtering out, gravity will begin to crush the core inward. This collapse will release a surge of heat so intense that it will push the sun's outer layers to a monstrous size. Our familiar yellow star will bloat into a red giant, its outer edge swelling to engulf the orbits of Mercury and Venus. Earth's ultimate fate hangs in the balance. While our planet might not be completely vaporized, it will be scorched beyond recognition, its surface melted into a global ocean of magma as it orbits within the sun's outer atmosphere. This red giant phase is the sun's final dramatic act of nuclear fusion. In its hot, compressed core, helium will begin fusing into carbon, but our sun is not massive enough to ignite the carbon, so this new fuel will burn in fits and starts, causing the star to pulse violently. With each pulse, it will eject more of its atmosphere into space. Eventually, all that will remain is the star's hot, dense core, exposed to the cold vacuum. This core, a white dwarf, will be surrounded by a magnificent, glowing shroud of its own expelled gases, a planetary nebula. For a brief cosmic moment, 10,000 years or so, this nebula will glow with ethereal colors, a final piece of stellar art visible from far across the galaxy. Then the gas will dissipate, leaving only the Earth-sized diamond of the white dwarf, a trillion-ton cinder of carbon and oxygen that will slowly cool and fade toward blackness over tens of billions of years. The sun's journey from nebula to white dwarf is a local and personal example of the universe's greatest cycle. Its future death is not an anomaly but a universal inevitability, a reminder that even the most constant presence in our sky is a temporary participant in an endless dance of creation and renewal. The frantic fusion race within a massive star is a desperate sprint against gravity. As each fuel is exhausted in the core, the star contracts, heats up, and ignites the next available element, building a layered structure like a cosmic onion. The outermost shell fuses hydrogen into helium. Beneath it, a shell fuses helium into carbon. Deeper still, carbon fuses into neon, then neon into oxygen, and oxygen into silicon. Each layer burns to support the immense weight of the layers above it, but this support is a fleeting illusion. Each successive fusion stage releases less energy than the one before it, and the star burns through these new fuels at an ever-accelerating pace. A star might spend millions of years fusing hydrogen, but only a few hundred years fusing helium. The carbon-burning phase may last just a few centuries. When it reaches the final stage, fusing silicon into iron, the star has mere days left to live. This is the ultimate dead end. Iron is the most stable nucleus in the universe, and fusing it does not release energy, it consumes it. So when an iron core finally forms at the star's heart, the central engine does not just sputter out, it catastrophically fails. The core becomes a power drain, instantly robbing the star of its last source of support against its own immense weight. In less than a second, this iron core, which can be as massive as our entire sun, collapses from a sphere thousands of miles wide to one barely 10 miles across. The star's intricate onion skin structure, built over millions of years, is now plummeting inward at a quarter the speed of light, heading for a collision with the newly formed, impossibly dense neutron core. This is the moment of no return, the instant that sets the stage for the star's final, glorious self-destruction, a supernova explosion that will blast the entire periodic table forged in its brief, brilliant life back out into the galaxy. For stars born with truly monstrous mass, the final act of collapse is so violent it bypasses a black hole entirely. Imagine a star so colossal it contains between 130 and 250 times the mass of our Sun. Deep within its core, the temperatures and pressures reach such an insane extreme that the very nature of light changes. the gamma-ray photons, which provide the crucial radiation pressure holding the star up, suddenly become too energetic for their own good. Their immense energy spontaneously transforms into matter, creating pairs of electrons and their antimatter counterparts, positrons. This pair production process is a catastrophic turning point. The radiation pressure that was supporting the star's immense weight suddenly plummets, like a support beam instantly turning to smoke. With that outward push gone, the core experiences a violent partial collapse. This implosion is not gentle. It slams the core's material together, raising the temperature to staggering new heights until it triggers the runaway fusion of oxygen. This is not a controlled burn. It is a thermonuclear bomb of unimaginable scale detonating deep inside the star. The energy released is so titanic that it does not just blow off the outer layers. It completely unbinds the entire star, blasting every last bit of it out into space in an explosion of pure annihilation. A pair instability supernova leaves absolutely nothing behind. No neutron star, no black hole, just an expanding cloud of stellar ash. These events are thought to be the fate of the universe's very first stars, the so-called population 3 stars, which were likely pure hydrogen and helium behemoths. Some astronomers speculate that the bizarre supernova known as SN 2006 Gi, an explosion 100 times more energetic than a normal supernova, might have been a modern example of this rare and spectacular death. This ultimate form of stellar suicide demonstrates the incredible diversity of cosmic endings, where a star's initial mass alone can script a final act of total self-immolation, a flash of light so powerful it erases itself from existence. When a massive star's core collapses with tremendous spin, its death is not a simple explosion but a focused detonation of pure energy. This is a hypernova, an event far more powerful than a typical supernova, and it is the engine behind the most intense blasts of radiation in the cosmos since the Big Bang itself, the long-duration gamma-ray burst. The key to this cataclysm is a rapidly rotating core. As this massive star collapses, its spin intensifies, preventing much of the infalling material from immediately vanishing into the newborn black hole. Instead, this material swirls into a vast, superheated accretion disk, a cosmic whirlpool of plasma orbiting the event horizon. The physics of this maelstrom, known as the Collapsar model, channels unimaginable energies into 2 narrow, opposing jets. These are not gentle outflows. They are beams of plasma accelerated to more than 99.9% the speed of light, drilling their way out through the star's remaining layers. If one of these relativistic jets happens to be pointed directly at Earth, we detect its focused fury as a gamma-ray burst, a concentrated flash of high-energy photons that can outshine every star in 1,000,000 galaxies combined for a fleeting minute. These long-duration GRBs are not isolated events. They are the herald of a supernova, a stellar death scream that precedes the optical brightening of the supernova explosion itself. This connection was confirmed dramatically in 2003, when the afterglow of a gamma-ray burst revealed the unmistakable spectroscopic signature of a supernova, proving that these incredible bursts are the final acts of the most massive, rapidly spinning stars. Their sheer luminosity makes them cosmic lighthouses, visible from the very edge of the observable universe. They illuminate the ancient gas clouds they pass through, allowing astronomers to study the chemical composition of the early universe and measure vast cosmic distances. The study of these events pushes the limits of our understanding, providing a direct window into the violent physics of black hole birth and the behavior of matter at near light speeds. In a hypernova, a star's death is not a dispersal but a final, focused shout across the cosmos, a beam of energy so concentrated it can be seen from billions of light years away. The chemical fingerprint of a star is its own unique autobiography, written in the language of elements. This fingerprint, what astronomers call metallicity, is the key that unlocks the history of our galaxy. It tells us not just about the star itself, but about the cosmic environment it was born into, a story of previous stellar lives and deaths. To understand this galactic history, scientists sort stars into three broad populations. Our own Sun is a member of Population 1. These are the metal-rich stars containing a significant fraction of elements heavier than hydrogen and helium. They are the younger generation, found predominantly in the chaotic, star-forming spiral arms of the galactic disk. Their relatively high metal content is a direct inheritance, proof that they formed from an interstellar medium already enriched by countless supernovae that exploded before them. Then we have Population 2 stars. These are the ancient elders of the Milky Way. They are metal-poor, containing only trace amounts of elements beyond hydrogen and helium. They do not reside in the busy disk, but instead orbit in the vast spherical halo that surrounds our galaxy and in the dense central bulge. Their frugal chemical makeup tells a story of a simpler, more primitive cosmos. They were born when the galaxy was young, from gas that had been seeded with heavy elements by only the very first few generations of stars. Studying these ancient suns is like finding a living artifact from the universe's childhood. But what about the very first generation, the ones that started it all? These are the hypothetical Population 3 stars. Theory tells us they must have existed, colossal behemoths composed of pure hydrogen and helium, the only elements available after the Big Bang. With no heavier elements to help radiate away heat during their formation, they could have grown to staggering sizes, hundreds of times the mass of our Sun. Their lives would have been spectacularly short, ending in pair instability supernova that utterly vaporized them, scattering the first metals into the primordial darkness. We have not yet definitively found a Population 3 star, as they all died long ago, but their legacy is written in the chemistry of the oldest Population 2 stars we can observe. By mapping the locations and metallicities of countless stars, astronomers act as galactic archaeologists. They can trace how the cycle of stellar death and rebirth has progressively enriched the galaxy over billions of years. Each new generation of stars forms from gas that is slightly more metal-rich than the last, building a more complex periodic table with every cycle. The presence of iron in the Sun, for instance, means it is a third-generation star at least, born from gas that was twice processed through the lives and explosive deaths of massive stars. This chemical evolution reveals that our galaxy was likely built from the inside out, with the oldest metal-poor stars forming first in the halo, and younger, metal-rich stars like our Sun forming later in the disk. Every star is a time capsule, and its light carries the ghostly imprint of the generations that came before, a living record of the universe's journey from simplicity to the rich chemical diversity that made our world and us possible. That early universe was a profoundly simple and empty place, a cosmos of pure potential. After the Big Bang's brilliant flash, the expanding universe contained only the two lightest elements, hydrogen and helium, drifting in the dark. There was no oxygen, no carbon, no silicon, and crucially, no dust. This pristine environment was the birthplace of the very first stars, a generation astronomers called Population 3. Without heavier elements to help radiate away heat, the collapsing clouds of gas could grow to staggering sizes. These first stars were not like our Sun. They were likely colossal behemoths, containing anywhere from 100 to 1,000 times the mass of our own star. Imagine a single star shining with the light of millions of our suns, a brilliant but fleeting beacon in the primordial dark. Their immense mass created ferocious gravity, driving the core temperature to extremes our sun cannot fathom. They burned their hydrogen fuel not for billions of years, but for a mere few million, living fast and dying young in spectacular fashion. For the most massive of these giants, death was an act of total self-annihilation. Their cores grew so hot that the gamma-ray photons, which provided the pressure holding the star up, spontaneously transformed into matter, creating pairs of electrons and positrons. This pair instability process catastrophically robbed the core of its support. The star's heart then collapsed violently, triggering a runaway fusion explosion that was so utterly complete it tore the entire star apart. In a pair instability supernova, the star did not leave behind a neutron star or a black hole. It was completely vaporized, its entire being blasted back into space. This was the moment the universe changed forever. Within that expanding fireball, the first heavy elements were forged. For the first time, the cosmos was seeded with carbon, oxygen, and iron, the very materials that would eventually form rocky planets and living organisms. This was the crucial first step in the cycle of chemical enrichment, the initial pollution of a pure universe that made all future complexity possible. The hunt for these elusive first stars is one of modern astronomy's greatest quests. Their light is so faint and distant that no telescope has yet definitively captured it. But the James Webb Space Telescope, with its incredible infrared sensitivity, is peering back into this cosmic dawn, searching for the unique chemical signature of a population, 3 supernova, or the indirect glow of their immense clusters. The death of these first stars was not an end. It was a necessary baptism by fire. Their explosive deaths fundamentally transformed the universe from a simple state of hydrogen and helium into a chemically rich and diverse cosmos. They laid the very groundwork for the second generation of stars, and eventually for the formation of stars like our own sun, around which a world like Earth and life like us could one day arise. Measuring the cosmos requires a ladder built from starlight, each rung a different method for reaching farther into the void. This cosmic distance ladder begins with simple geometry like stellar parallax, which works for our galactic neighbors. But to leap across millions or billions of light years, astronomers need something far more powerful, a beacon of known brilliance. They need a standard candle. These are celestial objects whose true, intrinsic brightness is predictable. By comparing that known luminosity to how dim the object appears from Earth, scientists can calculate its distance with remarkable precision. The universe provides these vital tools through the predictable lives and deaths of certain stars. Cepheid variable stars are one such rung on the ladder. These are aging, unstable stars that pulse rhythmically, growing brighter and dimmer over days or months. In the early 20th century, astronomer Henrietta Swan Leavitt discovered a direct relationship between a Cepheid's pulse rate and its true brightness. A Cepheid with a long, slow pulse is inherently more luminous than one with a short, rapid flicker. This was a revolutionary key. By simply measuring the period of its pulse, astronomers could know the star's actual wattage. In the 1920s, Edwin Hubble used this key to unlock the greatest astronomical mystery of his time. He identified Cepheid variables in the faint, fuzzy Andromeda Nebula. By measuring their apparent dimness and applying Leavitt's period luminosity law, he calculated a distance so vast that Andromeda had to be a separate galaxy, a twin of our own Milky Way. This single discovery instantly expanded the known universe, revealing it to be a realm of countless galaxies. But Cepheids have their limits. To probe the deepest reaches of space, we need an even brighter standard candle. This is where stellar death provides the ultimate tool, the Type Ia supernova. As we learned, these explosions occur when a white dwarf star is pushed over its mass limit, triggering a runaway thermonuclear fusion. Because this limit is always the same, and the exploding object is always a carbon-oxygen white dwarf of a specific composition, the peak brightness of a Type Ia supernova is incredibly consistent. They are the universe's 100-watt light bulbs. When astronomers detect one in a distant galaxy, they know its true, staggering luminosity. The incredible faintness of that light after its billion-year journey across space becomes a direct measure of the vast distance it has traveled. It was by using these stellar explosions as mileposts that two teams of researchers made a Nobel Prize-winning discovery in the late 1990s. They found that the most distant Type Ia supernova were fainter than expected. The universe was not just expanding, the expansion was accelerating, pushed by a mysterious force we now call dark energy. The predictable death of a white dwarf star, therefore, is far more than an endpoint. It is a fundamental instrument of discovery. These stellar candles illuminate the scale of the cosmos, trace the history of its expansion, and reveal the hidden forces that dictate its ultimate fate. Our entire cosmic map, from the nearby stars to the edge of the observable universe, is drawn using the light of dying suns. Every star you see is dancing to the pull of an invisible partner. This cosmic choreography is governed by dark matter, the mysterious substance that makes up the vast majority of all mass in the universe. Though it does not emit, absorb, or reflect any light, its gravitational influence is the fundamental force that sculpts the cosmos. Without this unseen framework, the grand cycle of stellar life and death would never have begun. The story starts with dark matter halos, vast, spherical clouds of this enigmatic material that began forming in the early universe. Their immense gravity acted as cosmic gathering points, pulling in the ordinary hydrogen and helium gas that filled the young cosmos. This was the essential first step. The dark matter provided the massive gravitational anchor, while the normal gas, able to radiate away energy, could cool down, condense, and eventually fragment into the first stellar nurseries. The properties of a dark matter halo directly dictate the fate of the stars that form within it. A massive, dense halo will pull in enormous quantities of gas, leading to a frenzy of star birth and the creation of a brilliant spiral galaxy. A smaller, more diffuse halo might only manage to form a few scattered stars or a faint dwarf galaxy. The distribution of dark matter even influences the very structure of a galaxy, shaping the majestic spiral arms where new stars are born and the vast halo where ancient stars reside. While dark matter itself never ignites into a star or explodes in a supernova, its gravitational hand is present at every stage. It dictates the rate at which gas flows into galactic centers, fueling bursts of star formation. It governs the motions of galaxies, causing them to collide and merge in events that trigger new generations of stars. The entire visible drama of stellar existence, from the ignition of a protostar to the final blast of a supernova, plays out on a stage that was built and is still held together by the invisible presence of dark matter. To truly understand the life and death of stars, we must look beyond the light. We must learn to see the dark architecture of the universe, the hidden framework that makes all this luminous beauty possible. That brilliant violence does not remain confined to a single point. When massive stars are born together in clusters, they die together as well, and their collective fury can reshape the galaxy itself. A family of these titans, known as an OB association, lives a short, spectacular life. Their powerful stellar winds blow like constant hurricanes, and their deaths as supernova come in rapid succession. Each explosion sends a shockwave slamming into the surrounding interstellar medium. When these shocks overlap and merge, they do not just create isolated remnants. They carve out a colossal cavity of million-degree gas, a structure so immense it can span hundreds of light years. We call this a superbubble, a cosmic hot air balloon blown by the combined breath of dying stars. The sheer energy is enough to push the surrounding gas outward, creating a dense, cool shell of compressed material that marks the superbubble's boundary. But the most dramatic events occur when these superbubbles grow so large that they rupture the galactic disk. The hot, pressurized gas within the bubble finally finds a path of least resistance, not sideways along the plane, but upward and downward, perpendicular to it. This gas erupts out of the disk in a titanic fountain, launching countless solar masses of supernova, enriched material high above the galaxy into the galactic halo. This is the galactic fountain, a vast, cyclical flow that constantly churns a galaxy's contents. The hot gas, now far from the dense disk, begins to radiate away its heat and slowly cool. Over millions of years, it condenses into massive, cold clouds that can no longer resist the galaxy's pull. They begin a long, slow rain back down onto the galactic plane, plummeting at supersonic speeds. This returning metal-rich gas splashes back into the interstellar medium, seeding it with the heavy elements forged inside the cluster stars and their supernova. We are, in fact, living inside one of these structures right now. Our solar system floats within a region called the local bubble, a vast cavity of hot, thin gas in our galactic neighborhood. This 500 light-year-wide void is believed to have been sculpted by a string of supernova that exploded over the past 10 to 20 million years. The shockwaves from those ancient stellar deaths cleared out the surrounding gas and dust, leaving us with a relatively clear view into the galaxy beyond. This grand circulation is the galaxy's way of stirring the pot. The fountain effect ensures that the ashes of dead stars are not simply dumped in one crowded neighborhood. Instead, they are lifted high and spread wide, falling back like a gentle, life-giving rain across the entire spiral disk. This rain enriches distant molecular clouds, providing the raw materials for rocky planets, and potentially seeding the birth of new stellar generations far from the violent clusters where their ingredients were first forged. This vibrant era of stellar creation we live in is a finite chapter in the cosmic story. The universe's great star-forming days are already behind it. Billions of years ago, galaxies were ablaze with the light of newborn stars, a period of intense and rapid fire creation. But that golden age has passed. The fuel for new stars, the vast reservoirs of hydrogen gas drifting between them, is gradually being depleted. With every new star that ignites, and with every old star that locks its material away in a white dwarf, neutron star, or black hole, the total amount of available gas diminishes. The rate of star birth across the cosmos has been in a slow, steady decline for over 10 billion years. We are living in the universe's mature adulthood, a time still rich with light, but one that is inevitably winding down. The great cycle of stellar death and rebirth will continue for countless eons as the ashes of supernova are recycled into new generations. But this process is not a perpetual motion machine. Each cycle is slightly less productive than the last, as more and more material becomes trapped in stellar graveyards from which it cannot easily return. The brilliant, short-lived giants that sculpt galaxies and forge heavy elements will be the first to vanish from the cosmic scene. Their era will end as the remaining gas becomes too scarce and diffused to form such behemoths. The final stars to shine in the universe will be the frugal red dwarfs. These small, dim stars are the ultimate cosmic misers, so efficient with their hydrogen fuel that they can burn for trillions of years. Long after every other star has died, the red dwarfs will glow with a faint, deep red ember in an increasingly dark cosmos. Their eventual extinction, trillions of years from now, will mark the end of the stellar era altogether. The universe will then enter a final, dark age, a quiet and cold expanse populated only by the fading remnants of a once vibrant past. This distant future makes our present epoch all the more remarkable and precious. We are alive during the cosmic noon, a brief, shining moment when the universe is still filled with a dazzling variety of stars, when supernova regularly light up the darkness, and when the conditions for life are possible. The endless cycle of stellar death and rebirth gives our cosmos its richness, but it also reminds us that this age of light is a temporary and spectacular gift. This precise cosmic choreography, spanning billions of years, raises a profound question. Why do the fundamental rules of our universe seem so perfectly arranged to allow for our existence? This line of inquiry is known as the Anthropic Principle. It suggests that the universe we observe must be compatible with the conscious life that observes it, and the stellar life cycle is the ultimate proof. The physical constants that govern nuclear fusion, from the strength of gravity to the power of the strong nuclear force, are balanced on a razor's edge. If gravity were slightly stronger, stars would burn too hot and fast, exhausting their fuel before complex elements could form. If the nuclear force were slightly weaker, hydrogen would never fuse into helium, and the universe would be a dark, starless void. Our cosmic timeline is equally critical. It took the long, slow lives of first-generation stars to forge the initial carbon and oxygen. It then required their violent deaths as supernova to scatter those elements into space. A second, and even a third, generation of stars had to form from this enriched material, with some living stable lives long enough for planets to coalesce and life to evolve on at least one of them. If the stellar life cycle were significantly faster, the galaxy would be a chaotic wasteland of constant radiation from endless supernova. If it were slower, the necessary heavy elements might still be locked inside the cores of long-lived, unevolved stars. We are here only because the universe operates on a specific, generous timescale with exquisitely fine-tuned laws. The iron in your blood and the calcium in your bones are not cosmic accidents. They are the products of a universe whose fundamental parameters allow for stars to live, die, and be reborn in a cycle that ultimately creates observers. Our very ability to trace this stellar genealogy, to look up at the night sky and understand our connection to the stars, is a direct result of that very same process. We are the universe awakening to contemplate itself, a fleeting thought made possible by an endless, element-forging dance. Our ability to trace this cosmic genealogy depends entirely on a suite of technological marvels that act as extensions of our own senses. Each stage of the stellar life cycle reveals itself through a different kind of light, and we have built specialized eyes to see them all. To find the cold, dark cradles where stars are born, we turn to radio telescopes. These massive dishes detect the long, faint waves emitted by molecules like hydrogen as they drift in the frigid emptiness of interstellar clouds, mapping the invisible raw material of future suns. Once a protostar ignites deep within its dusty cocoon, its warm glow is best seen in infrared light. Observatories like the James Webb Space Telescope are designed to peer through the obscuring dust, revealing the violent, hidden nurseries where infant stars are just beginning their lives. For the adult stars and the glorious planetary nebulae they leave behind, our own eyes and optical telescopes like Hubble show us their brilliant visible light, painting the cosmos with the familiar colors of glowing hydrogen and oxygen. But to witness the true violence of stellar death, we must look to the highest energy forms of light. X-ray observatories like Chandra see the multimillion-degree gas blazing within supernova remnants, the shocked and heated debris from a star's final explosion. They also reveal the searing accretion disks of matter spiraling into black holes. Gamma-ray telescopes capture the even more extreme bursts from magnetar flares and the hyper-energetic jets of hypernova. Yet, simply seeing the light is not enough. The true magic lies in a technique called spectroscopy. By carefully spreading a star's light into a rainbow-like spectrum, astronomers can read it like a cosmic barcode. Dark lines etched across this spectrum reveal the star's precise chemical composition, telling us which elements are present in its atmosphere. The exact position and width of these lines disclose the star's temperature, its density, and even how fast it is moving toward or away from us. This is how we know the Sun is made mostly of hydrogen and helium, and how we can detect the faint whisper of iron in the light of the most ancient stars. Our entire understanding of the stellar life cycle, from a cloud's first collapse to a white dwarf's final cool down, is a mosaic pieced together from observations across the entire electromagnetic spectrum. We are not just watching the stars, we are learning to read the story they have written in their own light. Yet for all we have mapped of this cosmic cycle, profound mysteries remain. The final, furious moment of a core collapse supernova still defies our full comprehension. Computer simulations show the shockwave stalling, unable to blow the star apart. What invisible physics, what hidden hand, revives this shock and powers the explosion? The answer likely lies in the ghostly neutrinos that flood from the collapsing core, or in the violent churning of the star's interior. But the precise mechanism is a puzzle we have not yet fully solved. This is not just one mystery, but a family of them. Why do some massive stars die as relatively dim supernova, while others unleash hypernova and brilliant gamma-ray bursts? What secret ingredient, perhaps rapid rotation or powerful magnetic fields, determines the final, spectacular form of a star's death? Even the corpses of these stars guard their secrets. Inside a neutron star, matter is crushed into a state we cannot replicate on Earth. Is it a soup of free quarks, a solid crystal of neutrons, or something even stranger? The true nature of matter at these densities remains one of physics' greatest unsolved problems. We also witness the universe's remarkable ability to create order from chaos. In the expanding fury of a supernova, amid gas heated to millions of degrees, microscopic dust grains of carbon and silicate somehow form. These are the very seeds of future planets. How do these delicate structures nucleate, grow, and most bafflingly survive the violent aftermath? It seems impossible, and yet we see this dust throughout the galaxy. Each of these questions represents a frontier. The quest to answer them drives the development of colossal telescopes, powerful supercomputers, and new ways of seeing the cosmos, from gravitational wave observatories to neutrino detectors. The universe, in its infinite complexity, is still whispering its deepest secrets. Our journey to understand the stellar life cycle is far from over. It is an ongoing story written in the light of dying stars and the silence of the dark matter that binds them. This grand cosmic cycle is our own origin story written in starlight. From the silent collapse of a dark nebula to the final, brilliant flash of a supernova, every step in a star's life is an act of cosmic alchemy, transforming simple hydrogen into the very elements that make our world and our bodies possible. We have traced this incredible journey, seeing how stellar death is never an end, but a dispersal, a scattering of enriched material that will one day coalesce into new suns and new planets. The iron that carries oxygen in your blood was indeed forged in the core of a massive star that lived and died billions of years before our sun was born. The calcium that strengthens your bones was created in the final throes of a red giant. Every breath you take fills your lungs with oxygen that was once the outer layer of a star. We are, in the most literal sense, the universe remembering itself, so the next time you gaze up at the night sky, do not see it as a collection of distant, static points of light. See it for what it truly is, a vibrant and dynamic ecosystem, a cosmic forge where stars are born, live, and die in an endless element-building dance. Their story of destruction and creation is our story too. If this journey through the universe's greatest cycle has sparked your curiosity, we would love to hear your thoughts in the comments below. And subscribe to continue exploring the profound mysteries of space together.